Inverse trig functions. Sine and sine inverse. If f of x is equal to sine of x is defined as a function from or to or being the real number set, then it is neither injective, as some horizontal lines intersect the curve at y equals sine of x more than once, nor surjective, as there are horizontal lines that do not intersect the curve at all. The dashed lines on the diagram below illustrate this. So we can see this red dashed line, the lower one, intersects the curve in 1, 2, 3, 4 places on the actual graph that we can see, but we know that the graph goes on forever to the left and forever to the right, so it actually cuts the curve in an infinite number of places. So the graph of y equals sine of x cannot be injective, as the horizontal line, this one here, intersects the curve in more than one place. And obviously we could draw on a few different lines. So if we were to draw a line across here, so along the x-axis, y equals 0, the same thing would happen. Along here, this could be minus 0.9, the same thing would happen. Then this red dotted line above does not intersect the curve at all. So this is possibly 1 on the y-axis. If this is just the graph of y equals sine of x, then this must be 1, the maximum point must be 1. So this could be 1.1, 1.2 maybe on the y-axis. Y equals 1.1 or y equals 1.2. And we can see that it does not intersect the curve at all. So the graph cannot be surjective either. Thus, this function is not bijective, because in order for the function to be bijective, it has to be injective and surjective. So this function is not bijective, and its inverse is not a function. We need the inverse to be a function. What we can do is restrict the domain and the codomain so that the resulting function is bijective. A long time ago, it was agreed that we would take the domain to be minus 90 degrees to 90 degrees, or minus pi over 2 to pi over 2, if working in radians, to form a bijective function. So the domain being the x values, or the input. Then the codomain, which was the same as the range, is minus 1 to 1. This gives the following bijective function. F of minus 90 to 90 maps to minus 1 to 1 maps to sine of x. The inverse of this is a function called the inverse sine function. And it's defined as follows. F to the power minus 1, so basically the inverse function of minus 1 to 1 maps to minus 90 degrees to 90 degrees maps to sine to the power of minus 1 of x, so the inverse function of sine of x. The diagram below shows the curves y equals sine of x and y equals the inverse of sine of x, as defined above. Recall that each is the image of the other under the reflection in the line y equals x. So here is the graph of y equals sine of x, and here is the graph of y equals the inverse sine of x. And we can see that one is the reflection of the other in the line y equals x. So this red line here is the line y equals x. So notice that we go up as far as 1 and minus 1 on the y-axis, and back as far as minus 90 degrees, and up as far as 90 degrees on the x-axis. So this is for the function of y equals sine of x. Whereas when we have the inverse function of sine of x, the y-axis goes up as far as 90 and down as far as minus 90 degrees, and the x-axis goes back as far as minus 1 and up as far as 1. This is why the inverse function of sine of x is only defined for x values from minus 1 to 1. So x values from minus 1 to 1. And has a value that lies in the range of minus 90 degrees to 90 degrees. So minus 90 degrees to 90 degrees. This is sometimes referred to as the principal part of the inverse sine function, and is why, for example, the inverse sine of a half equals 30 degrees, and not any other angle whose sine is a half. Your calculator is aware of this definition. So, for example, if we were to go to a half on the x-axis on our inverse function, which is about here, if we were to draw a line up and a line across, we would get to about 30 degrees. So this is a half, we draw a line up, a line across, and we get to 30 degrees. So basically, whatever value you put in place of the x, so if instead of a half you went with 0.75 or a third, whatever you were to put in place of the x, so long as it's in between -1 and 1, you will end up with a value corresponding on the y-axis of between -90 and 90 degrees. Cosine and cosine inverse. Similarly, f of r maps to r of x maps to cos of x is not a bijective function, but the function f of 0 degrees to 180 degrees maps to -1 to 1 maps to cos of x is a bijective function. Its inverse is the inverse function of -1 to 1 maps to 0 degrees to 180 degrees maps to the inverse function of cos of x, which is a function called the principal part of the inverse cosine function. The diagram below shows the curves y equals cos of x and y equals the inverse of cos of x, as defined above. So for y equals cos of x, we have x values from 0 degrees to 180 degrees, and y values from 1 down as far as -1. Whereas with the inverse function of cos of x, we have x values from -1 to 1, and y values from 180 degrees down to 0 degrees. This is why the inverse of cos of minus a half is equal to 120 degrees, and not any other angle that has its cosine equal to minus a half. You should check that your calculator agrees with this. So if we were to go to minus a half on the x-axis for the inverse function of cos, which is about here, and draw a line up and a line across, we should get to 120 degrees. So this is minus a half, we draw a line up and a line across, and we get to 120 degrees. Tangent and inverse tangent. In the last chapter, we saw that f of x equals tan of x was defined only for the real number set without plus or minus 90 degrees, plus or minus 270 degrees, ... and that its range is the real number set. To form a bijective function, we take the domain to be x values between minus 90 degrees and 90 degrees, but not including either of them. So x values greater than minus 90 degrees but less than 90 degrees, which can be written as the open interval minus 90 degrees comma 90 degrees. Then the codomain is or the real number set. The bijective function is then f of minus 90 degrees to 90 degrees maps to or of x, or being the real number set, maps to tan of x. The inverse function is then the inverse function of or maps to minus 90 degrees to 90 degrees maps to the inverse function of tan of x, called the principal part of the inverse tangent function. The diagram below shows the curves y equals tan of x and y equals the inverse function of tan of x, as defined above. So here we have y equals tan of x. We have x values from minus 90 degrees up as far as 90 degrees. And the y-axis goes up as far as or, the real number set, so it includes all real numbers. And this is the inverse of tan of x. And the x-axis is now the real number set, so it goes on forever in either direction. And the y-axis goes up as far as 90 degrees and down as far as minus 90 degrees. Hence, for example, the inverse of tan of 1 is 45 degrees and not any other angle whose tan is 1. So if we were to go to the inverse graph of tan and we were go to 1 on the x-axis, let's suppose that 1 is here. If we were to draw a line up and a line across, we would get to 45 degrees. So let's say this is 1 on the x-axis. We draw a line up and a line across and we get to 45 degrees. So there may be other angles who give us a tan of 1, but the inverse tan of 1 can only give us 45 degrees. And that's because we've restricted the domain and the codomain.